Hi, welcome. This is Robert Bolaños. This is the analysis and design of a flyback, how to use the PWM model, part 16. Okay, specifically, I'm going to talk about how to use a transformer to sense the current in a primary. Okay, so to do that, I want to go ahead and do another example. Okay, and it's going to be different. In this case, we're going to go ahead and simulate something at a much higher power. We're going to go we're going to increase the voltage 24 volts, 1 amp, which is 24 watts, and the second output is going to be 24 volts, also at 1 amp, 24 watts. Okay, and then what we're going to do is we're going to go ahead and see what is the power at our sense resistor. Okay. So if you get all the equations that I have covered throughout the lectures, you can make an Excel file. Here I have V minimum. Let me see if I can do this. Okay, so V minimum, I'm going to keep it 24 volts, and here I have it where I can have either 1, 2, 3, up to 4 output values. And here's my current, so I'm going to go ahead and set this 24 volts, 1 amp, 24, and 1 amp. And of course, you can put your maximum duty cycle. I'm going to go ahead and put 0.45, efficiency of 80%, frequency, and so forth. Okay. Now these V sense, this is the current sense. Okay. So although it says V, it's actually the current sense, but I'm actually measuring voltage. Okay. And now these in the green are my output or my results. So in this case, I'm going to have 48 watts, and with the efficiency, that turns out to be about 60 input watts. And then I have my average current, my peak current, my RMS current, and then this is the T on, the time that the MOSFET is on. And what I really need is my inductor value. In this case, to achieve 60 watts of input power, I need 9.7 microhenries. Okay. Now this sense resistor, depending what I put here, if I want 1 volt at my PWM, then I would need a 0.09 ohm resistor to give me approximately 1 volt at the I-sense line. Okay. But since I want a little bit of margin, maybe like 10% margin, I set it to 0.9. Okay, anywhere from 0.8 to 0.9 is good. So this calculates what's the R sense is going to be. Okay, and then it calculates the power. Okay, so let's go ahead and do that. Okay, my primary inductance is set to 9.7, and since it's 24 divided by 24, let me go ahead and change this to 1. I'll set this to 1 as well. And let me see, my R sense is 81, and here is 0.01. Okay, and I've labeled the voltage across my current sense resistor as sense. Okay, and I want to measure the power So in TopSPICE, they have the calc function, which you can give an equation, and this equation says that the power, in this case it's going to be the power through the resistor, is the current, and I put a negative I, it's the negative current. In other words, it's the current that is flowing through the resistor times the voltage across the V sense, which is voltage across the resistor. So that should give me the instantaneous power. Okay. So go ahead and run it. Okay, here I have my two outputs. It's regulating at about 24.2, so that looks good. So then we can go ahead and look at our V sense. It's supposed to be close to 0.9 volts. It's actually 0.778. Okay, round it up to 0.8. And the current, this is the current. Let me go ahead and put maximum. Maximum current is 11.2. Let's see what would calculate it here. 11.1. That's pretty good in agreement. Okay. So now we want to check the power that has been dissipated by the sense resistor. The spreadsheet calculates that it's 1.5. Okay. So this is the instantaneous power through the resistor. So you can see that it has a peak current, max, as a peak current of 10 watts through the resistor. That's quite a bit of current. Okay. So to see what the RMS current, or the actual average power, you go to power and then you get the mean, and the actual is 1.29. So let me go ahead and put this 1.29 watts. So that's what was simulated. Simulation. Okay. So that's quite a bit of power. Okay. Let's see how much power it actually is. Okay. So 1.29 divided by 48 output watts times 100, that's almost 3%. It's actually 2.6%. So that's quite a bit of power just being dissipated by your sense resistor. Okay, so what can you do to make this more efficient? Okay, well, to make it more efficient, you can use a current transformer. Let me backtrack a little bit. 0.081, a comment that I want to make is that as you get below 1 ohms, then the resistor values are not as great. You would have to parallel higher value resistors to get the value that you want. So once you go below 1 ohm, it's harder to find values that correspond to the value that you need. Okay, so that's a concern. So you might not have a value that is selectable. You may have to make one by paralleling resistors. So that's where a current transformer may come in, and it's very useful. Okay, so let's look at let me go ahead and put this. See, this is 81. So how much power was dissipated? I'll put 1.25. Yep, 29. Okay. 1.29. Okay. So what can we do? Okay. We can actually add a transformer. And we can use it to sense the current. Therefore, it's a current transformer. Okay. How does this work? Well, keep in mind that the current going through the primary is going to look like this. And we said that the peak is 11.1. 11.1. Okay. So we have that. So as that current, and I go ahead and put the dot here, dot. So as this current flows in that direction, this current is going to flow out in that direction. So basically, if you monitor this current, it'll be a representation of your primary. So this would be your pri, and this would be your sec. Okay. So they're proportional to each other. How? Or they're proportional to the transformer equation. This is the general equation that you use for all transformer, namely that the turns of the primary times the current in the primary is equal to the turns of the secondary times the current in the secondary. Okay, so how do we use this? Well, what we want to do is this I sec is what's going to flow through the diode. It's going to flow through this direction, so that develops a positive voltage across the resistor. Okay. Now this is it's called a burden resistor, and it's used to reset the transformer. And typically this is much higher than the sense resistor. So we can say R burden is much greater than the R sense. Why? Because you want as much of this current to flow through here and not flow through here. The only current that you want flowing through here is when it reverses, okay, or resets. So that's why we want this statement there, that you want this or this to be much bigger than this. Okay. So since we want this current, that's your I sec or I secondary. So if you solve for that, that means you're going to have the N primary and secondary times I primary. Okay. So this is the equation that you use. Okay. Okay, so let's simplify this a little bit. We already know what this value is. We know that this is 11.1 amps. Okay. And when you do or you build a current transformer, what you want to do is you want this to be one turn. You don't want 10 turns or a lot of turns because it adds resistance. So basically you want this to be a low value, low resistance and inductance. Okay. So since this is one turn, That means that this is 1 turn. Okay. And most current transformers, the secondary is anywhere from 50 turns to 100 turns. I like to use 50 turns. So in this case, this goes to 50. So then now ISEC becomes basically I primary divided by 50. So in this case, the peak current through the secondary is divided by 50 should be 11.1 divided by 50, which is 555 milliamps. That means that you're going to have a waveform that looks, current waveform that looks like that. 555 milliamps. Okay. So now you want your V-sense waveform to look like as close to it as 0.1 when you have this waveform. So now you do R sense divided, or actually is equal to 0.9 divided by your ISEC, which we've already calculated. Let me see what we get. So it should be 0.9 divided by 0.555. Okay. Let's see. I get 1.62. 2. Let's see. Okay, I think I did something wrong. Okay. I believe I made a mistake here. So 11.1 divided by 50, 222. 222 milliamps. 222. 222. Okay. So 0.9 divided by 0.222. So I get a R sense of 4.05 ohms. Okay, and if you come over here, right here, this is for my transformer 404 of 4.05. Okay, so let's see how this is implemented. Okay, and here's the transformer. Okay, again, this is basically a couple inductor. I'm using the L4 and L5 as the transformer. I use K2 to couple L4 and L5 together. In this case, I'm using the coupling coefficient of 1 to simplify things. Okay, and for the inductance, I went ahead and go ahead and I set the inductance to 1 microhenry. And since I want 50 turns, I set NR to 50. So basically NR2 times NR2 times L current, meaning that whatever this is, it's going to multiply times 2 squared to give you the approximate inductance value. So this does it automatically. So all you have to do is define as L current and NR2, and you basically have your turns ratio already set. Okay. Now this is your R burden resistor, and let me go ahead and rename it as burden. Burden. And if you notice, it's 3K versus 4 ohm. That satisfies the condition that I had mentioned, that the burden had to be much higher than the R sense. Okay, so most of the current is going to go through here, and I set it to 4.0. Go ahead and just set the 0.05. Okay, so same inductance, change the turns ratio to 1. Okay, now I have the results. Okay, let me go ahead and come up here. That looks good. We're at 24 volts. Okay. And if we look at the V sense line, we want it close to 0.9. This is the V sense. So go to position, maximum, and 797, basically 0.8. So that's close enough. So I have a little bit more margin than I need. I can increase the R sense. That way this goes up a little closer to 0.9, but that's fine. And again, the current, primary current, is 11.4. So you can see that it's regulating correctly, and we achieved the same current. Now we also went ahead and did the same thing here to calculate now the current through the R sense resistor. Even though it's a much higher resistor, the current is lower. Okay, so we did the power, the calc statement in TopSPICE, which is power is equal to the current through the sense resistor, times the voltage across the resistor, which is current through this resistor times the voltage across it. And if we look in here, and remember the current was 10 amps on the first example. Now the peak current, I go up here, is actually, instead of having 10, we only have 208 milliwatts of power. That's a big reduction. So now we can go ahead and take the average or the mean, and I'm only wasting 25 milliwatts of power. So 25 milliwatts of power. Okay, simulation. Okay, my I put it right there. Okay, so if I use just a regular sense resistor with no current, the power wasted in the R sense resistor, even though it was 81 milliohm, is actually 1.29 watts of power that was wasted. But if I use the current transformer, then the power is reduced from 1.29 all the way to 27 milliwatts. Okay, so that's a big reduction in power. Okay, that's almost a watt. That's almost a watt, 1.2 watts of power saved. That's quite a bit. That's almost 3% of your total power. So that's one of the good reasons that a lot of people use current transformers. Plus, if you notice, the resistor is no longer below 1 ohm. It's a much higher resistance. So the selection available to you is much greater. Okay, so again, this is one of the advantages of using the current transformer to sense your current through the primary. Alrighty, if you have any questions or comments, you can email them to rbola35618@aol.com. If you like the video, found it useful, go ahead and give me a thumbs up. And if you think of any other people that would benefit from these videos, please share my link to them. Thank you very much.